Let me ask you something that might bother you. What if I told you that the most important question ever asked about quantum mechanics was asked by a man everybody says got it wrong? That the person who saw the deepest crack in the foundation of modern physics, who pointed at it and said, look at that, was ignored for 30 years. And that, when the dust finally settled, when someone finally checked, it turned out the crack was real. It was exactly where he said it was. The man was Albert Einstein. And the thing he saw, the thing nobody wanted to deal with, is still there, still unresolved, right now, today. And almost nobody talks about it honestly. By the end of this lecture, you are going to understand what Einstein actually said about quantum mechanics. Not the cartoon version, not God does not play dice, the real argument, and you are going to see why it matters, why it shook the foundations of physics, and why it reveals something about nature so strange that most physicists would rather just not think about it. Let's start somewhere simple. Let's start with a coin. I flip a coin. It lands in my hand. I close my fist. Now, before I open my hand, is the coin heads or tails? You say, well, I don't know. Could be either one. Fine. But you believe it is one or the other, right? It's heads or it's tails. You just don't know which the information exists. It's sitting there in my hand. You're just ignorant of it. That's a perfectly reasonable thing to believe. That's how the world works, as far as you've ever experienced it. Now let me ask you a stranger question. What if I told you that according to quantum mechanics, before you look, the coin is not heads and it is not tails? It's not that you don't know. It's that there is no fact of the matter. The coin is in some kind of ghostly combination of both, and only when you open your hand and look does it snap into one answer. Does that bother you? It should bother you. It bothered Einstein. It bothered him enormously, and the reason it bothered him is not because he was old-fashioned or stubborn. It's because he understood something about that claim that almost everyone else missed. See, here's the thing people get wrong about Einstein and quantum mechanics. They tell you this story. They say Einstein couldn't accept randomness. He wanted a clockwork universe. He said God does not play dice, and that was that. He lost the argument to Niels Bohr, and physics moved on. End of story. That is not what happened. That is a fairy tale, and it does a tremendous disservice to one of the sharpest minds that ever lived. What Einstein actually argued was far more subtle, far more dangerous, and far more interesting than I don't like randomness. Let me tell you what he really said. Einstein had no problem with the mathematics of quantum mechanics. Let's be very clear about that. He helped create it. He's the one who said light comes in packets. He's the one who explained the photoelectric effect. He got the Nobel Prize for quantum physics, not for relativity. So when people say he didn't understand quantum mechanics, that's absurd. He understood it perfectly well. What he questioned was not the math. He questioned what the math was telling us about reality. And there's a crucial difference between those two things. Let me show you. Suppose I have a theory that predicts the weather. It says there's a 70% chance of rain tomorrow. Tomorrow comes and it rains. Great, the theory worked. But now I ask, did it rain because there was genuinely a 70% chance built into nature? Or did it rain because of specific air pressure, specific humidity, specific wind patterns, and my theory just wasn't detailed enough to figure all that out? Was the 70% a fact about the world, or a fact about my ignorance? That's the question Einstein asked about quantum mechanics. And it's a perfectly legitimate question. It's maybe the most important question you can ask about any theory. Quantum mechanics tells us that an electron doesn't have a definite position until you measure it. It gives you probabilities. You might find the electron here with 40% probability, over there with 25%, somewhere else with 35%. And the standard story, the one Bohr and Heisenberg promoted, says those probabilities are fundamental. There's nothing deeper. The electron genuinely doesn't have a position. It's not hiding. It's not secretly somewhere and you just can't see it. It literally does not have a definite position until you look. Einstein said, wait a minute, how do you know that? How do you know there isn't some deeper description, some more complete picture where the electron does have a definite position and your theory just can't tell you what it is? That's not an unreasonable question. That's a scientific question. And for a long time, most physicists just shrugged and said, who cares? The predictions work. But Einstein cared. He cared because he wanted to know what was real. And he fought for this point over and over in some of the most dramatic intellectual duels in the history of science. At the Solvay conferences in Brussels, where the greatest physicists in the world would gather, Einstein would show up with a new thought experiment every morning. He'd come down to breakfast, and he'd say to Bohr, consider this. Imagine I have a box with a clock and a shutter, and I release a photon at a precise time, and Bohr would go pale. He'd spend the entire day in a panic, pacing around, talking to everyone, trying to find the flaw. And by the evening, Bohr would have an answer. Sometimes a brilliant answer, sometimes a surprising answer. But the debates were fierce, and they were real. The thing that's remarkable is that every single one of Einstein's objections was genuinely deep. These weren't silly mistakes. Bohr had to work hard to answer them. And in some cases, the answers Bohr gave were, frankly, not entirely satisfying. They worked mathematically. But they left a philosophical residue, a feeling that something had been swept under the rug. And there's a wonderful irony in one of these debates. Einstein came up with a thought experiment involving a box of light designed to show you could violate the uncertainty principle. And Bohr refuted it by using Einstein's own general theory of relativity against him. The man who challenged quantum mechanics was defeated by his own greatest achievement. That's the kind of thing that only happens in real life. You couldn't put that in a novel, nobody would believe it. But Einstein didn't give up. He never gave up, because he wasn't trying to prove quantum mechanics wrong. He was trying to understand what it was really saying. And that's a crucial distinction. Now, you might think this is just philosophy, just two guys arguing about interpretation while the equations do the heavy lifting. But Einstein was cleverer than that. He didn't just argue philosophically. He designed a trap, a logical trap. And in 1935, with his colleagues Boris Podolsky and Nathan Rosen, he sprung it. This is the famous EPR argument, Einstein, Podolsky, and Rosen. And let me tell you, it is one of the most beautiful arguments in the history of physics. Not because of the math. The math is simple. It's beautiful because of the logic. Here's what they did, and I'm going to explain it carefully, step by step, because this is the heart of everything. Imagine you have two particles. Let's call them particle A and particle B. They interact with each other, and then they fly apart. One goes to the left, one goes to the right. They travel very far apart, miles apart, light years apart, if you like. Now, quantum mechanics says these two particles are entangled. That's a word Schrödinger actually coined, not Einstein. But Einstein is the one who saw the implications. What entanglement means is that the quantum description of these two particles is linked. Their properties are correlated in a very specific way. Let me give you a concrete example. Suppose the total spin of the two particles is zero. Spin is a quantum property. Don't worry too much about what it is physically. Just think of it as a kind of internal rotation, like a tiny gyroscope that can point either up or down. If the total spin is zero, that means if particle A is spinning up, particle B must be spinning down, and vice versa. They're always opposite. Always. That's the correlation. Now here's where it gets interesting. According to quantum mechanics, before you measure, neither particle has a definite spin. Particle A is not up and it's not down. It's in that ghostly combination. Same for particle B. Only when you measure one of them does it snap into a definite state. But, and this is the key, the moment you measure particle A and find it spin up, you instantly know that particle B is spin down. Instantly. Even if particle B is on the other side of the galaxy, you didn't touch particle B. You didn't send it a signal. You didn't do anything to it. But now you know its spin, with certainty. Einstein looked at this and said, fine. So by measuring particle A over here, I can determine the spin of particle B way over there without disturbing particle B in any way. That means particle B's spin must have been determined all along. It must have been real before I looked, because I didn't do anything to it. I couldn't have created its spin by measuring something else far away. That would mean my measurement sent some kind of instantaneous signal across the universe, faster than light. And nothing travels faster than light. You see what he did? He used quantum mechanics' own predictions to argue that there must be more to the story. If the correlations are real, and you can learn about a distant particle without touching it, then that distant particle must have had a definite state before you measured. Which means quantum mechanics, which says it didn't, is incomplete. There are hidden variables, some deeper reality that quantum mechanics doesn't describe. That's the EPR argument. It's not, I don't like randomness. It's a precise logical argument. Either quantum mechanics is incomplete, or measuring one particle instantaneously affects another particle far away. Einstein thought the second option was absurd. He called it spooky action at a distance. So he concluded quantum mechanics must be incomplete. Now wait, let's pause here and make sure everyone is on the same page. Let me say this as simply as I can. Imagine I have two gloves, a left glove and a right glove. I put each in a box without looking. I mail one box to New York and one to Los Angeles. Now I open the box in New York and find a left glove. Instantly, I know the glove in Los Angeles is a right glove. No spookiness, no magic. The gloves were always what they were. I just didn't know until I looked. Einstein said that's what's happening with quantum particles. The spins were always determined. Quantum mechanics just doesn't tell you which is which until you look. Like the gloves. Nothing spooky. And honestly, that sounds perfectly reasonable. That sounds like common sense. And for nearly 30 years, most people thought either Einstein was right or that the question was unanswerable and therefore not worth worrying about. Bohr gave a long, somewhat convoluted reply that many people found hard to follow. And physics moved on. People used quantum mechanics to build transistors and lasers and didn't worry about what it all meant. But here's the thing. Here's the hidden gap. The gap that Einstein saw and everybody missed. His argument rested on an assumption, a very reasonable assumption. An assumption so obvious you might not even notice you're making it. And the assumption was this, that the world is local. What does local mean? It means that what I do here right now does not instantaneously affect something far away. Effects travel, they propagate. If I push a ball, the ball rolls and then hits another ball. The influence travels from one place to the next. It doesn't teleport. That's locality, and it's not just common sense. It's built into the theory of relativity. It's one of the deepest principles Einstein himself discovered. Nothing travels faster than light. Influences propagate at finite speed. Einstein's argument was essentially quantum mechanics is either incomplete or it violates locality. And since locality is sacred, quantum mechanics must be incomplete. And for 30 years, that's where things stood. A stalemate. Nobody could figure out how to break the tie. You had Bohr saying quantum mechanics is complete and you just have to accept it. You had Einstein saying it can't be complete because that would violate locality, and nobody had a way to test who was right. It seemed like pure philosophy until 1964. That's when a quiet Irish physicist named John Bell changed everything. And what he did was extraordinary. He found a way to test Einstein's assumption. He showed that the question wasn't philosophy, it was physics, and it had an answer. Here's what Bell realized. If Einstein is right, if there are hidden variables, if the particles have definite properties all along, like the gloves in the boxes, then the correlations between measurements on the two particles have to obey certain limits. There are specific mathematical inequalities, specific numbers that the correlations cannot exceed. These are called Bell's inequalities. But if quantum mechanics is right, if the particles genuinely don't have definite properties until measured, and they're truly entangled, then the correlations can exceed those limits. Quantum mechanics predicts stronger correlations than any local hidden variable theory allows. Let me say that again because it's crucial. Bell proved a mathematical theorem that says if the world is local, if Einstein is right that there are hidden variables and no spooky action at a distance, then the correlations between measurements on entangled particles are bounded. They can only be so strong. But quantum mechanics predicts they're stronger than that bound. So now you can do an experiment. You set up two entangled particles. You measure their spins at different angles. You compare the correlations, and you check, do they stay within Bell's limit, or do they break through it? This was actually done. The most famous experiments were by Alain in Paris in 1982, though there were earlier ones too, and the results were clear, crystal clear. The correlations broke through Bell's limit. Quantum mechanics was right. Nature violates Bell's inequality. And let me tell you something about those experiments, because the details matter. One of the things Einstein might have said is, well, maybe the particles are communicating somehow. Maybe there's some signal we haven't detected traveling between them. So Aspect designed his experiment to close that loophole. He set it up so that the choice of what to measure on each side was made at the very last instant. So fast that no signal traveling at the speed of light could possibly get from one detector to the other in time to influence the result. And even with this safeguard, the correlations were still there, still exceeding Bell's limit, still matching quantum mechanics perfectly. Later experiments pushed this even further. They put the detectors farther apart. They used random number generators to choose the settings. They even used light from distant quasars, light that had been traveling for billions of years, to make the random choices. The idea being that those photons from ancient quasars couldn't possibly have been influenced by the experiment. And still the correlations held. Still Bell's inequality was violated. Every single time. The experimental verdict is as close to certain as science gets. Whatever's going on, it's not a fluke, it's not an artifact, it's not a loophole, it's real. Now, what does that mean? Let me be very careful here, because this is where people get confused and where all sorts of nonsense gets said. What it means is that at least one of Einstein's assumptions was wrong. Either the particles don't have definite properties before measurement, or measuring one particle does affect the other one instantaneously, or both. The simple glove story doesn't work. The world